Okay, thank you for inviting me to this conference. I'm excited to be here, my old alma mater. I'd like to talk to you today about one of the three Exascale co-design centers that the Office of Science at DOE is supporting. This is the Center for Exascale Simulation of Combustion and Turbulence, or otherwise known as XACT. I'm the director of the center, and the center is comprised of 6 national labs and 5 university participants. And it's a 5-year program, $20 million in total, and we're about midway through the second year of the program. So let me give you a little bit of motivation for why we have this center and why Exascale for combustion. So in the combustion area, we're trying to predict the behavior of evolving new fuel streams in different combustion scenarios, especially working with fuel-efficient new advanced engine concepts for transportation as well as for power generation, gas turbines for power generation. And we want to do these calculations, simulations at realistic aerothermochemical conditions. What I mean by that is at real turbulence conditions, at high pressures, and in the temperature environments that are relevant to these kinds of devices. And so in order to do this in an efficient manner and help optimize the co-design of both engines as well as fuels, we think that exascale computing can play a very significant role. So in our co-design center, we're focused on a particular numerical method, direct numerical simulation. In DNS, we resolve all of the turbulence scales. There's no closure for the turbulence, but there are still models inserted for representing the chemical physics, chemistry, and for molecular transport properties, for radiation, and so on. So in addition to being able to perform these first principles of DNS with high sufficient chemical fidelity to tell apart the different effects of the fuels and how they couple strongly with turbulence, we also are concerned about capturing the uncertainties in the thermo-chemical properties. So for example, how do errors propagate when you have uncertainties in key rate constants, for example, for the reaction rates in a turbulent simulation? And then I want to put the caveat or disclaimer that in our center we're not focused on complexity of geometry, but we're more concerned with the underlying physics associated with turbulence chemistry coupling. So our first task we had was to define what are the exascale use cases. So where do we project these calculations to be? And so the kinds of examples I've pointed out here, the first one here is homogeneous charge, compression ignition. There's a move in the transportation community to move more towards premixed compression ignition concepts to give you the higher efficiencies and the lower emissions. And so this is kind of there are various flavors of this. There's spark-assisted compression ignition, homogeneous charge, and various flavors. But in essence, it's a chemical engine. It doesn't have a spark to tell you when to start combustion. It doesn't have a direct injector, but it relies on the movement of the piston in some kind of isentropic compression process to bring on to the point where you can self-ignite through auto-ignition. That controls the timing. But the trick and challenge here is to how to tailor the charge, the fuel-air mixing together with EGR, exhaust gas recirculation in the cylinder, in order to get the proper burn rate so that you don't end up driving a very noisy engine that has a very high pressurized rate. And so controlling ignition and burn rate is the holy grail of that problem. Second problem here has to do with turbulent jet flames that are swirling. These are low swirl injector gas turbines and we're concerned with hydrogen-enriched fuels for pre-combustion carbon capture in a staged lean premixed combustion, and so issues here have to do with flame stabilization and emissions. Another category is dealing with lifted diesel jet flames. In this case, we're looking at lifted diesel jet flames at high pressure that are trying to propagate upstream into a soup of cool flame low temperature ignition radicals. And so how does a flame stabilize there? What position does it stabilize? That affects sooting processes, for example, that occur downstream of that point. In all of these problems, we want to look at UQ with respect to chemistry and transport properties. And we've extrapolated that our current petascale capabilities show that these cases will require exascale level resources. So why then do we need to do co-design? Well, if you look at where computing has been in the last couple of decades, the old constraints that we've tried to optimize around are kind of listed here. We've been really trying to get maximized throughput where flops is the biggest metric. And the main limitation has been, for performance improvement, has been peak clock frequency. As I said, the cost has been mostly associated with optimizing the floating point operation speed. And the growth in concurrency has been somewhat modest for adding parallelism by adding nodes. The programming model for locality has been primarily MPI plus X, where X could be something like OpenMP or CUDA or something else. But this kind of presumes uniform costs both within a node as well as across the entire machine. The memory scaling has been more or less constant for quite some time. We've maintained the same byte to flop ratio for capacity and bandwidth. And we've kind of been fortunate to have more or less a uniform system performance. However, as we move towards exascale, there are a new set of constraints that have come into the picture, the most important of which is power, and this is the primary design constraint is power and not flops. And the main cost now is associated with how far you have to move data on a chip or across the machine. So we need to optimize to minimize data movement. So data movement dominates the entire picture. The other aspect is because the clock frequency has leveled off, the only way we're going to get concurrency is to have exponential growth in the number of chips, up to about 1 billion chips to get to exascale. And with that comes a whole host of problems with resiliency. We also have to reason about data locality and possibly about the overall topology. And memory scaling has kind of reached a limit too. The compute is growing 2 times faster than the capacity or bandwidth of memory. So memory is shrinking. And furthermore, the memory, there's less likely to be global hardware support for cache coherency. There's all kinds of heterogeneity, so uniformity is out the door, both in terms of the hardware and also in terms of performance. Non-uniformity on the system is going to increase enormously. So if you want to operate, for example, near voltage thresholds, there's going to be a lot of variability in processors' speeds across the entire machine. So you can't count on uniformity anywhere. So what does this imply? Well, it implies that future algorithms, programming environments, runtimes, and hardware have to first be able to express data locality, often at the expense of flops and speed. We need to allow expression of massive parallelism. We want to minimize how far we move data and how often we do global synchronization in the codes. And then we need to have some methodology for detecting and addressing faults, which are going to occur much more frequently than they do now. So with this context, the goal of our center on co-design is to consider all aspects of combustion simulation. Clear down from the formulation of the problem, we should probably be rethinking how we formulate the problem, as well as the basic math algorithms not only for the solver, but also for the analytics, for the UQ, and how they play together, to the programming environments that we use to express these algorithms on these complex machines, as well as the hardware characteristics that are needed to enable these calculations on these complex architectures. So in our co-design center, we interact closely with the vendors to help define the hardware requirements that are best suited to our field. We are working with computer scientists on programming environments, requirements, and runtime systems, and with the applied math community on developing future locality-aware algorithms for PDEs, UQ, and analytics. And in our center, we've been working on new methods like spectral deferred correction algorithms, and also talking with folks like Mike Minion on parallel and time types of algorithms as possible extensions of where we're going to go in the future. So the petascale codes that provide a starting point in our co-design process are two. S3D is a code that I've written in my group over a long time with BES support. It's a compressible reactive Navier-Stokes equation, uses higher order explicit finite difference methods for both the time discretization as well as a fourth order 6-stage Runge-Kutta method. It's explicit, has a detailed treatment for kinetics and molecular transport. We also have a dilute spray model in there, a thermal radiation model in there, soot model, and it's been programmed a bunch of different ways, including MPI, MPI plus OpenMP, OpenACC with pragmas for the GPUs, and most recently, and what I'd like to talk about in a little bit, is its implementation within a Legion compiler and runtime system. LMC is a code written by John Bell at Lawrence Berkeley Labs. It's a low Mach number code that exploits the separation of scales between acoustic waves and convective motion. It's a second order projection formulation, also treats kinetics and transport, and it uses a block structured adaptive mesh refinement approach. Also has various programming models that it's been written in. But our expectation is that at Exascale, we're going to have to rewrite the entire code base. So block structured AMR, we need that to move up in pressure because of the disparity in scales. The scales of flames and ignition phenomena get down to about a micron, and there's quite a difference in scales between the turbulence scales and the flame scales. And block structured AMR reduces the number of degrees of freedom needed to represent the solution, and it presents a natural hierarchical parallel model that's well suited to these multi-core architectures. Just one word about in situ uncertainty quantification guided by analytics. So here, as I pointed out earlier, we're trying to look at uncertainties and reaction rates characterizing rare events like ignition extinction that control fuel efficiency and emissions with respect to uncertainties in the chemical and transport parameters. Here, working with Bob Moser, we're trying to solve the adjoint equations backwards in time about the forward primal state at all times. And so that presents an enormous data management problem because of the sheer volume of data required to be kept in memory or storage. And in our center, we've come up with a unique approach that exploits space-time locality guided by on-the-fly feature detection and tracking that identifies the regions of interest for which to do the UQ. And so we're also developing topological segmentation and tracking algorithms that will be done in situ, and these typically have graph-based algorithms quite different than PDE solve algorithms. Just to point out, the petascale workflow won't scale in the sense that the I/O bandwidth won't keep up with the computational throughput, and so the notion of post-analyzing, computing, post-analyzing, reading your data back into a machine and analyzing further will fail at the exascale. And so a lot of the workflow has to be moved into the machine and done in situ. A word about programming environments that are critical to performance. These are, I think it's already been pointed out that what we really need is to come up with a programming model to express locality and independence, and to be able to program these block-structured partial differential equations for high performance, scalability, and portability on heterogeneous machines with a lot of variability, but still enable the domain scientists to read their code. In co-design, our process is to actually consider mini apps or proxy apps. These express the pain points for performance in certain parts of our application, and to hide all of the non-essential bits. And at the bottom of the stack, we have architectures, and we have proxy machine architectures that describe some of the key important machine attributes for performance. And so then we can start to reason with the proxy apps and the proxy architectures through modeling and architectural simulation. But we still need to have full apps to actually make sure we haven't lost some information along the line. So in our center, we've created a number of proxy apps. You can download them from our website, exactcodesign.org. And I won't list all of these proxy apps, but they have to do both with the solver as well as with the UQ workflow. And so I just want to say, skip over some of this, but I want to say a few words about Legion and its in the context of combustion. So we've been working with Alex Aiken and his PhD students here, Mike Bauer, Sean Treichler, and Elliot Slaughter, on talking about applying Legion to express task and data parallelism for S3D. And so in Legion, they describe the data in terms of these logical regions that are arrays of objects that have no implied layout or implied location. And these are described by index space, a set of keys expressing the array pointers to different locations, say on a mesh. And these objects then have field spaces, such as temperature, pressure, and so on. And you can subdivide these, or partition these logical regions into subregions, and you can also partition the field space, and you can do this in an AMR context recursively. So in addition to these logical regions, Legion also has a hierarchical tree of tasks. And the Legion tasks specify how to use a region, which fields to access and use within a given region, and it specifies through type systems very tight access controls by whether you can read the data, read write, or do some kind of reduction on it. And so, for example, here I showed two tasks that both access region R, but they're disjoint data because task 1 is accessing only field A and task 2 is accessing field B. And so they could, Legion would reason that these tasks are independent and could be run in parallel on separate processors, node 0 and node 1. Now if task 1 now needs to operate with field B, then Legion realizes that there is a dependence between the two tasks, and it would automatically schedule task 1 sequentially before it executes task 2 on node 1, and it would automatically copy the information from field B to task 2 before it executes on node 1. So, and then another thing that Legion does is it assigns mapping to happen at runtime, and it's not decided where to place the data on memory or which tasks to run on which processors until runtime does that. And the runtime assigns these processors and tasks to processors, regions to memory, and it provides a nice mapping API for the programmer to customize a mapper, for example, in their specific scientific domain. So here, we're just in this cartoon illustrating the various tasks that are mapped to the x86 CPU cores as well as to a GPU core, and the different data regions, logical regions that are mapped to memory. So we thought we'd try this on S3D, which is a my DNS code. It's about 100,000 lines of Fortran coupled with MPI currently. And it uses an explicit method. It has lots of phases, lots of potential parallelism that can be exploited. And so in Legion, they found that 97% of the work is done in the advancement of the right-hand side, which advances the conserved variables in time. And so if you look at the full volume and the solution at time t, denoted in the red box, it carries all the conserved variables, might be 100 independent variables. And then basically the output of that is a time advance over one substage of an RK of these conserved variables. In addition to that basic I/O function of this right-hand side function task, it needs to save a bunch of state information such as the temperature, properties like thermoconductivity, viscosity, and so on. And then if you look more deeply within the right-hand side function, there are a bunch of subtasks associated with computing things like the specific volume, temperature, pressure, reaction rates, and so on. And those require inputs from the previous state, the time at the current state, the solution vector, and it writes out a bunch of intermediate variables or intermediate state. And so Legion reasons about all of these tasks and the data, and then it does further data parallel, recognizes that you can chunk up the volumes into and do many of these tasks in parallel. So that's what that is. And then if you look at so that's kind of describes a little bit in detail the task and data parallelism within the right-hand side function. But if you look at the overall code, as shown by this task graph, this is one call to right-hand side function as seen by the Legion runtime systems. And the arrows or lines that you can faintly see here indicate the true data dependencies. This is the smallest chemical mechanism possible, 9 species for hydrogen, and we're really looking at things like heptane with 100 species. So the graph gets much wider. And this graph is then instantiated on a bunch of different pieces of data where you're trying to do this in data parallel as well as task parallelism. But I could never extract this amount of parallelism by doing it by eye. You really need a machine or a runtime system to help you with this. So yeah, manual task scheduling of this would be really hard. Okay, and then finally we've also looked at, this is another picture of the Legion execution system on a given node, showing the chemistry work on the GPUs, the stencil work on the CPUs, and then the Legion runtime running on top and doing dependence analysis tasks when it spawns off a task. And just kind of say one more last thing, which is that Legion doesn't treat the tasks, it treats the tasks as opaque boxes, and so it really still relies on us to make these leaf tasks that are computationally intensive, such as chemistry evaluation, to make those run fast. And so one more thing that we've been working on is a domain-specific language compiler called Singe. This is really Mike Bauer's work for the chemistry kernels. And in our field, we already have a DSL, which we didn't even know we had, called ChemKin, which parses and takes tables of inputs for chemistry, thermodynamics, and transport variables, and emits fast code for computing the reaction rates. And so Singe here, what he did that was very clever was he found a way to make Singe work very well on a GPU. Most GPU programming models emphasize data parallelism, and it's not always the best choice for performance. And in this particular case, we have a large working set size per point because of the chemistry, where it requires something like 600 double precision reaction rates per point, whereas the GPU register files on a chip only hold 128. And so we would have register spillover and all sorts of memory contention if we were to have to fission this piece of fast kernel, right? And so we don't want to fission the kernel, but we want to come up with a better way to make use of the GPU. And so what Mike did was to invoke warp specialization, which leverages the knowledge of some of the underlying hardware. And these GPU warps execute streams of 32 wide vector instructions, come in 32 threads per warp. It's a data parallel unit where all threads in a warp execute the same program. But he realized that each warp could run a different piece of the code, different computation, and in this way leverage task parallelism. And so different warps here then do different computations on the same data, and this allows us to keep much of the data in memory and while keeping more of the processors busy. And so we could fit then large working sets on the chip. And so the kinds of things that we divided up the chemistry kernel, different warps compute different aspects of it. And so the upshot is that in doing this kind of programming model exploration, we found that the chemistry kernels could run 10 times faster than they currently run, and that the overall production code S3D runs 30% faster on a single node than the OpenACC version with a very large mechanism. And so they're currently in the process of scaling that up to the full size of Titan and looking at multi-node evaluations. So I'll stop here. Sorry I've gone over.
Thank you.
Okay.